Today we are going to see the concept of a transfer function, and to be able to do that we are going to use the mechanical system that is part of an accelerometer device that we are studying in our class. The idea behind a transfer function is to establish a relationship between an output and input. So let's see how that applies to this example. So, okay, we have this device on the left hand side, which you see it has let's see here. You have an input in here that is from a device or the grounding, let's say, and you have an oscillator here, a simple oscillator with a damping and a stiffness and a mass. In this particular case, when the base moves, it's the same as if we move this base in here up, and then this is going to move up and down. What I have done is I have isolated just the oscillating part, the mechanical side, because what happens is when this moves inside, it actually presses on this piezoelectric device that produces a voltage, and that is connected to an electrical system. But because we are trying to study the mechanical example and use that for the transfer function, then it follows that we should define what the input is and what the output is. Okay, so in here we are going to define, let's say for the sake of example, I am going to put a force in here. I could put a force or a velocity input in here, but let's do a force input in here to illustrate what the concept is. So let's say if this is F. So this is my input to the system. Okay. In this particular case, I would like to know what is the input force. What is the, you can say, what is the force on this damper, for example? As if this moves, what is the force produced over here? Okay, so in this case we have that the output in this case that we want is force on the damper in there. This is what we would like to know. So we make a definition as to what is the transfer function. Let's put in here transfer function is a relationship between the output, which would be Ft, F of the damping, in relationship to the input in here. This is what we're going to call the transfer. Let's call it transfer function like that, so that we don't confuse with the transformer element. So this thing, I reiterate, this is, we are defining what the output is, and we are relating it to an input. So the concept of a transfer function is always a relationship between an output and an input. So why do we do this? We do this with some purpose, because we can always say that the output is equal to the transfer function times the input. Okay, so let's say that our objective is to find out this force that are over here. That's my output. This is my input. We want the relationship between these two in such a way that if we have that relationship, we could actually use this concept in here. Isn't it true that if I know the so-called transfer function and I know the input, we should know the output? That's the idea. So it's a very simple concept, what the transfer function is. However, there's more to it. We need to introduce, in this case, the Laplace transform, because it's a nice way of finding these transfer functions, and it gives us an opportunity also to study the frequency domain of systems. So let me explain you what we're going to do. You know how I like steps? So maybe we can write some steps on the right hand side over here. If we have a space in here, you can say, why don't we do this? We call it the steps to find the transfer function. Steps to find the transfer function. Okay, what would be the first step? Step number one, I'm going to say, is we are going to derive the equations of motions. That means, obviously, in the time domain. Okay? The second step we're going to do is we are going to apply the Laplace transform. We are going to see in a moment what that is. And then step number 3, find the ratio, the output divided by the input. This is the so-called transfer function. Yeah? Okay, let's do it for this example. How do we actually do this? The way we do this is we are going to find the differential equations of the system. So step 1, okay, has to do with the differential equations. So you see here, we could say that the if we make a free body diagram of the mass in here, how what forces act on this? So first you would say you have the weight, which is mg. Okay, if I actually move this up, I'm going to get opposition forces. One that says this is k times y, and then this other one which is going to be b times y dot, right? So if we establish the differential equation of the system, this is going to be you apply the Newton's equations. The summation of the external forces is equal to mass times the acceleration, like that, right? So, and here we say we need to define which way is positive. So I'm going to define it positive upwards. So isn't it true that we have the forces are minus mg, and then you will have minus k times y minus b times y double dot. This is equal to mass times the acceleration in the y direction, like that. Okay? So we know now that if we compress the spring, we are positive, but if we stretch the spring, it's negative. So this is my differential equation, and in here we need to oh, see, I have a little mistake in here. This is not double dot, but just dot, one dot. Okay, so this is the differential equation. So we have done step number 1. Okay, I'm of the idea that we should take a look at the differential equation in here and see what's the best thing to do. Like when we do for block diagrams, we leave it like this. I would say we could leave it like this for now and then apply the Laplace transform. We need to add the external force also that we have in here. This, we have decided that this is F, and this is going to be in the positive direction. So we could just add it over here. Okay, so this is my system differential equation. In fact, let's properly label it. This is what I would call the second order differential equation. Okay, so what is my output in here? Let's just keep track of what the output is. Let's define what is my output here. My output is the force acting on the damper in here, which is B times X times Y dot, right? This is my output, okay? So we are going to introduce the Laplace operator. The Laplace operator says that d dt is equal to s. This is our operator in there. So if you have something like y dot, which is dy dt, this is the same thing as s times y of s, like that. And if you have y double dot, this is dy dt of this, right? So this is going to be the operator s times what I have written before, y of s, like that. So this is s squared times y of s. Yeah? So continuing with our derivation of the transfer function, we are going to go to step number 2. See that I outline up there? It says apply the Laplace transform. So let's do that. We need to apply the Laplace transform to the differential equation, is what we mean. So how would we do this? I'm just going to say step 2. apply the Laplace transform to the differential equations. And so now we are going to say that this is like f of s minus mg minus k times y of s. Actually, we use capitals. Let's just be consistent about that so that we, instead of, we don't confuse with them. And I am going to use over here too, okay? And then minus b times s times y of s. This is equal to m times s squared times y of s, like that. So what you can do in this case is we can write this in different ways. We can put it all to, well, let's just do it slowly, okay? F of s minus mg is equal to ms squared plus bs plus k times y of s, isn't it true? I just move these terms to the right hand side, like this one over here, and also the other one, this one. If we do that, we obtain what I just did. Okay? So, isn't it true that see, f of s is the force, relates to the displacement over here, and okay, so we have applied the Laplace transform. Now the output here, see, this is, from here we could conclude that y of s is equal to f of s minus mg divided by ms squared plus bs plus k, right? So if this is true, we now have the output that we're looking for. Remember, the output right here is the output fd. So the output in here was the damping, which was b times y dot. So this is the same thing as b times s times y of s. See? So from the first equation, we have this, and now this is over here, see? So if we say that if we can substitute this into here, you're going to have that Fd is equal to B times S times this F of S minus Mg divided by Ms squared plus Bs plus K. Okay? Yeah? So in here, we want the relationship between f d of s in relationship for f of s. This is the transfer function that we are looking for. Okay, so we ignore this input for now because we only going to reduce the to so you could say we relate relating one input to one output. You have that this is going to be the transfer function that we want over f of s is your you will have this is we are going to obtain it from here, right? So this is going to be ignored. So you're gonna have f of this is going to be b times s divided by ms squared plus bs plus k. So and this is my transfer function. See, using this equation in here and moving this to the other side like this, I obtain this equation. Yeah? So this is my transfer function. This is the transfer function. You can have the transfer function with relation to the other input, to mg, also to the weight. But we have obtained the one that we need as we set up to do at the beginning. But how do you actually enter this into MATLAB? How do we enter this into MATLAB? So we have right now the transfer function. Perhaps to make it a little more understandable, because it comes from here, and we are not taking into consideration the weight. Perhaps if I went too fast on that, what I'm trying to say is this is FD is equal to B times S times F of S like this, divided by ms squared plus bs plus k. And with this, if we move this one over here, we are going to obtain this equation. So I hope with that clarifies it a little better. But how do we actually enter this into MATLAB? I think that's, and how do we actually do something with it? I think that is the important question right now. We have established the relationship between one output, which is in this case the force, and one input, one output, which is the force on the spring, and the input, which is the f of s. So here we ignore the output, the input of m of g, because we could obtain another transfer function that relates this to the velocity to this force. But in this particular case, we're interested in the relationship between the damping force and the input force. If we were to find the transfer function with respect to the weight, which we can, then f of s, then the the other would have to be ignored, f, the input f. So in this case, we ignore the weight and then we let the other stand, and that's how we got the transfer function. So let's just put some numbers in here and see how do we enter this into the transfer function in MATLAB. I am going to say, like, for example, that b is equal to 2 and that m is equal to 3, let's say. That, well, we already said b is equal to 2 and that k is equal to 5, let's say. So we have a transfer function that looks like this. It says b, which would be 2 times s times 3 s squared plus bs plus k is 5. Yeah, this is the transfer function that we need to enter. Remember, another thing that I said is that the output is equal to the transfer function times the input. So if you give it like a step input like that, yeah, we should be able to know what the output is. So why don't we do that? How do we enter this into MATLAB? This is the next step. So we go to we open MATLAB and we run MATLAB, and what we are saying is we want to be able to put this transfer function into MATLAB, the one that you see here. So we could do this by establishing the numerator of this fraction, because always it has a numerator and denominator, and entering the coefficients of the polynomial. 2 is the polynomial of power 1, and of course 0 is the power of, we don't have s. Okay, so this is like so we don't have a constant term. So this is the numerator, and then we're going to say the denominator is going to be equal to 3 is the coefficient, then power 2. We need this guy. How come now I didn't get the correct? Did I? Yes, I did. This is the correct parenthesis. So this would be 3, and then a 2, and then a 5, then close the parenthesis. And I got the denominator. So g is going to be defined as the transfer function between the numerator and the denominator. And lo and behold, I have my transfer function as I have it on the left-hand side, right? Do you see it there? See, this is the transfer function right here, which is exactly the same as this one. Now, this transfer function is basically the system itself. And I should be able to say what is the output to a step input of this transfer function, g, and I say, okay, click, and MATLAB goes and actually does it for me. So you could see that now we have a new way of simulating things by finding the transfer function of a system, right? There is a couple of plots that we use besides this time, the step input plot, to test the transfer function. But I think I wanted you to see how you obtain the transfer function, how you enter it into MATLAB. And so the question is raised, could we actually make a bone graft model of this system and obtain the transfer function that way? The answer is yes, but that would be the subject of another little video. So we'll stop for now.